it looks like I'm not going to get out of doing a video review. I keep getting requests for an overview. We had it before break. I was like, why am I even doing this before break? Like, you're going to want it after break. But I did it anyways. Maybe it was good practice for me. Let's see. First of all, let me see if I can get this here. You can see as far as what we're looking at, chapter 20, 20-1 through 20-6. 20-7 we eliminated, so I probably should change that. Just the fact that solenoids are just repeated loops and what kind of magnetic field it would create would be good to know, but honestly, that's just from my perspective. I don't know any particular AP problems that would have that. And then we get into 21-1 through 21-3, so it was a little bit shorter than what my original list had. I think it's a really cool section. The fact, like, the crux of this is an induced EMF. And if you guys remember what an EMF is, right? It's that fancy E, right? That fancy E, which is just a voltage, right? It's a potential difference. And I love that I just tried to spell that. Anyways, all that to say is the whole crux of this, of learning about current carrying conductors creating a magnetic field, and that magnetic field, if you've got two current carrying conductors, you've got a force, and then if we can get that magnetic field to change, we can create that potential difference. So let's just start from the beginning and go from there. These videos can only be 10 minutes long, so we'll see where we get, right? I don't sound as cool as Mr. Bozeman. I don't have great, I guess, graphics like Bozeman, but hey, I'm in Florida and I'm just working through this. So when we get into 20-1, let's take a look at that. 20-1 was really about magnets and magnetic fields, and a north and a south pole, right? And let's try to remember which way these magnetic field loops go from magnet, right? So it should be going out of north into south, right? If I were going to do this, right? Out of north into south, and they go through this here. Now, if I were to put a compass on one of these, right? If I were to put a compass on here, my little north arrow, right, would be pointing towards this. If I put a compass right here, it would actually be tangent to the line, okay? So if the line is straight, it's going to be linear with it, but if it's curved, it's going to be tangent to that line. Another aspect we've kind of briefly talked about, what if we broke up that magnet into 3 spots? We had that north and you south. You've got this property where you've got this basically dual poles, polar, north pole, south pole. The magnets themselves maintain this property of polarity, which is kind of cool. So really that's all I had for 20-1. 20-2 and 20-3 are related. And 20-2 was just observing a phenomena. When we would put current, right, through a conductor, right, there was a field that was created, right? And so the video that we had just showed a current carrying conductor through, I guess, like iron shavings or filings within a fluid, right? And you saw it create these loops around, okay? So it created these loops. That does not show up in the video at all. Those are round loops. Maybe I'll do it darker, right? Loops of field, okay? Now 20-3 really got into it. So 22 was just observing the phenomena. 20-3 was observing, or actually had values to it, right? Values for, well, what was it for? 20-3 really was if this created a magnetic field, right? It's creating a magnetic field and you put it inside another magnetic field, you're going to have polarity. For instance, on this current carrying conductor, right, if my current is going up, we use our right-hand rule, right? We use our right-hand rule, and if it's in the plane, if the conductor were in this plane, which way would the field go, right? So right-hand rule, current, it wraps around, right? So it's coming out, and we use dots, right? When it's coming towards us, and then X's going away. Now, they're all gonna be circled, right? And I'm just lazy on showing that. But that's intended to be like an arrow. The point of the arrow is coming towards us, so it's a dot. The tail of the arrow is going away from us. So with my right-hand rule going around this current, I flip the current, and it swaps the direction of the field on either side. Okay? So 20-3 is about the force. If I were to put this current carrying conductor within a magnetic field, right, then we get a force. And we did that. We had a magnet, a little U magnet, and then we put some batteries, right, and created a circuit, and we saw it kick out, right? So you've got a magnetic field, right, and that was B, right? Now, is that a Tesla? I think it's a Tesla. Okay. And they also have Gauss's, which is a fraction of a Tesla, I think at 10 to the negative fourth. We've got this magnetic field right there. And if we put a current carrying conductor, sorry, I'm just going to put this in here. Right. Now the current carrying conductor, this current is conventional current. So if protons, right, could move in this current or in this conductor, that would be the direction of its movement. Electron flow is the opposite direction, but we're all based on conventional current. It's just what they chose years ago. Years ago. Okay? So we talked about the force that would occur on this. Okay? That force, let's see if we can remember that equation. The force is definitely going to be impacted by how much length is in that, how much current, and the strength of the field. So if I have current, length, and field strength, right, this would be basically what impacts, would be the proportionality. And what did they do? I think they called this theta, okay? So what would be its maximum force would be at what degree, okay? Maximum force would be at what degree? So if we tilted it perpendicular to it, it would be at its max. So is that sine or cosine where it is equal to 1.0, right? So this is a max, right? But force is equal to current, the length that's within the field lines, right? That strength, and sine of theta, right? If theta equals 90, right? Sine of theta equals 1, okay? So that's basically 20-3 was the force that occurred on a current carrying conductor in a field. Now, the last question is going to be, and I only have like 15 seconds to go or 30 seconds to go, is which direction is it going to go? And that's when we use our right-hand rule. So force, this field direction is the palm, the fingers are the direction of the current, and my thumb is the direction of the force. So if my field is this way, my current is up on the page, my force is going to be into the page. Okay? So right-hand rule goes to conventional current. So that's 20-1 through 20-3, and from there we will work on 20-4 and on. Maybe. Maybe.